All right, let's talk about something we see every day, but maybe don't really think about. What actually happens when you mix two liquids together? Why do some things just blend perfectly and others, well, they just don't? It turns out there's this hidden world of pushes, pulls, and what you could almost call molecular friendships that governs everything, from the cocktail you're sipping to some really serious life or death situations. Today, we're pulling back the curtain on those hidden rules.
So, to get started, let's look at two totally different people in two totally extreme environments. Now, on the surface, their problems seem completely unrelated, but they are tied together by one single, powerful principle of physics.
Okay, so on one hand, picture a scuba diver going deep into the ocean. Under all that immense pressure, the nitrogen gas from their air tank starts to dissolve into their bloodstream. Now, if they come up too fast, that pressure disappears, and the nitrogen literally starts bubbling out of their blood inside their body. It's an incredibly painful, dangerous condition we call the bends. Then, on the other hand, you've got a mountain climber way up at high altitude. They have the exact opposite problem. The air pressure is so low that not enough oxygen can dissolve into their blood, which leads to weakness, confusion, a state called anoxia. So high pressure causes too much gas to dissolve. Low pressure causes too little. What's the common thread here? What is the invisible force connecting these two life or death scenarios? Well, the answer lies in a really fundamental property of all liquids, and understanding it is the key to this whole story.
To really get what's happening with our diver and our climber, we need to introduce what's basically the golden rule for how liquids behave, and it all kicks off with a concept called vapor pressure.
At its heart, this is a pretty simple idea. Every liquid has molecules that are just itching to escape and turn into a gas. Vapor pressure is simply a measure of that desire to escape. A liquid with a high vapor pressure, like gasoline, evaporates really easily. You can smell it right away. But something with a low vapor pressure, like cooking oil, not so much.
So back in the 1880s, a French chemist named François-Marie Raoult figured out this beautifully simple relationship for this whole thing. We call it Raoult's law, and it's our golden rule. It basically just says that in a well-behaved, ideal mixture, the amount of pressure each liquid contributes is directly tied to how much of that liquid is actually in the mix. Simple, right?
So what did he mean by mole fraction? Don't let the name scare you, it's just the chemist's way of saying percentage by molecule count. So if we have a solution that's 75% liquid A molecules and 25% liquid B molecules, then the mole fraction of A is 0.75, and for B, it's 0.25. That's it.
And this is Raoult's law in action. It's super intuitive. Since liquid A makes up 75% of the mix, it contributes 75% of its potential pressure. Liquid B is 25% of the mix, so it brings 25% of its pressure to the party. The total pressure you get above the solution is just those two parts added together. In a perfect world, it's all just simple math.
But, and you knew there was a but coming, right? The real world is rarely perfect. Most liquid mixtures do not follow Raoult's law exactly. They break the rules. And when they do, things get really, really interesting.
We call a mixture that follows the law perfectly an ideal solution. But the vast majority of mixtures are non-ideal. And the reason for all this comes down to how the molecules actually feel about being next to each other.
It really all comes down to a balance of forces, or as I like to think of it, molecular friendships. In an ideal solution, the attraction between two different molecules, let's call them A and B, is pretty much the same as the attraction between two of the same molecules, like A and A. Everybody just kind of gets along equally. But what happens when they don't?
Well, you can get what's called a positive deviation. This happens when the different molecules don't really like each other as much as they like hanging out with their own kind. A classic example is ethanol and acetone. So in pure ethanol, the molecules are held together pretty tightly by something called hydrogen bonds. But when you add acetone, its molecules get in between the ethanol molecules and, well, they break up the party. They weaken those bonds. This makes it easier for molecules to escape the mixture, so the vapor pressure actually goes up. It deviates positively from what Raoult's law would predict.
And of course, the exact opposite can happen too. This is negative deviation, and it's when the different molecules actually attract each other more strongly than they attract themselves. Take chloroform and acetone.
When you mix them, they can form a brand new hydrogen bond between them that didn't exist before. This extra clinginess makes it harder for molecules to escape the liquid, so the total vapor pressure goes down, giving us a negative deviation.
Now, this rule-breaking behavior leads to one of the absolute strangest phenomena in all of chemistry. It creates mixtures that are, for all practical purposes, impossible to separate using normal methods.
These things are called azeotropes. Now, to get why they're so weird, you have to remember how distillation is supposed to work. You boil a mixture, and the vapor becomes richer in whichever component boils more easily. That's the whole point. But an azeotrope just thumbs its nose at that rule. It's a mixture where the liquid and the vapor have the exact same composition. It's almost like the mixture has decided to become a brand new single substance.
And this has massive real-world consequences. For instance, if you take a mixture of ethanol and water, say from fermenting beer or wine, and you try to purify it by distilling it, you're going to hit a wall. You can't get to 95% ethanol no problem, but you can't get to 100%, ever. Why? Because at a mix of 95% ethanol and 5% water, the mixture forms an azeotrope.
Let's just walk through that. You heat up your 95% ethanol solution. It starts to boil. The vapor that comes off is also 95% ethanol. So you can condense that vapor all you want, you just end up with the same 95% mixture you started with. The process just stalls. It's a physical dead end, all because of those molecular friendships we were talking about.
Okay, let's zoom out one last time. It turns out that this business of lowering vapor pressure is just one part of a bigger family of properties. And the secret to all of them is not about what you dissolve in a liquid, but simply how much of it you dissolve.
Think about it this way. Imagine dissolving a solid that doesn't evaporate, like salt or sugar, into water. Those little salt particles, they're not going anywhere, but they're taking up valuable real estate on the water's surface. They're basically acting like tiny little roadblocks, getting in the way of the water molecules that are trying to escape into the air. With fewer on-ramps to the gas phase, the overall vapor pressure of the whole solution drops. This whole phenomenon is a perfect example of something called a colligative property. I love that name. It comes from the Latin words for to bind together, because all of these properties are linked by one single unifying principle. They only depend on the number of solute particles, not what they are. 1,000,000 salt particles will have almost the exact same effect as 1,000,000 sugar particles. This family has 4 members. We've got the lowering of vapor pressure, which we've been talking about. This directly causes the boiling point to go up and the freezing point to go down, which is exactly why we salt icy roads in the winter. And finally, it affects osmotic pressure, which is absolutely critical for biology. But the crucial point, the one thing to remember from all of this, is that it's all about the count. It's the quantity of stuff you dissolve that matters, not its identity.
So, we started this whole journey with divers and climbers, and we ended it all with a simple pinch of salt. What we've seen is that these simple rules about molecular attraction and concentration, they have these truly profound effects on the world. From industrial chemistry to literally keeping us alive, these properties are absolutely everywhere. And it just leaves you wondering, if a pinch of salt can so fundamentally change the very nature of water, what other invisible forces are shaping the world around you right now? Thanks for joining us on The Explainer.